Welcome back, everyone. We got ourselves a algebraic based question, so let's dive in. The statement reads, check equation 12.29 using equation 12.27. This only proves the invariance of the scalar product for a transformation along the x-axis, but the scalar product is also invariant under rotations, since the first term is not affected at all, and the last three constitute the three-dimensional dot product, A dot B. By a suitable rotation, the x direction can be aimed any way you please. So for the four-dimensional scalar product, it is actually invariant under arbitrary. So the four-dimensional scalar product is actually invariant under arbitrary Lorenz transformations. All right, so what we need to do is find a suitable substitute or suitable rotation to show this. So is the 4D scalar product invariant? Okay, well, we need to show that it stays unchanged. So let's write out what this invariant product is. Remember that when I have the four vectors in the A, I have to have the contravariant vector and the covariant vector, and we have to multiply them. But in order to do that in a scalar way, what we have to do is change the contravariant to the covariant, the covariant to the contravariant, which requires us to change the sign on the zeroth component. So what we're trying to do here is see, does this four-dimensional scalar product equal the transformed scalar product? That's the goal here. So we have the left-hand side being the untransformed and the right-hand side being the transformed. And let's see what we can find out. Well, we know how the zeroth component transforms for A, B, and the x component for A1, B1. But clearly we see that the 2 and 3's don't do anything. Remember, y bar goes to y, x, and then z bar goes to z. But what we see here is that when we FOIL out and distribute everything in these brackets, we get a gamma squared that can be factored out of the the transformation of the zeroth coordinate. And now you see we can distribute and we get A naught, B naught, and then we get a minus beta, A naught 1, B naught, or B1. And that cancels over here with the transformation of the first coordinate. So you see we get a lot of things that can come together, but the things that stay uncanceled are these kind of squared terms. So 0, 0, 1, 1, 0, 0, 1, 1. That being said, if we look at the diagonal of this thing under its transformation rule, everything on the diagonal stays, everything outside would cancel in the summation. That being said, we still have to be careful with these gammas because we still have to distribute and put them to rest with these beta terms. So let's see how we can do that. So of course the second component and third component stay as normal, y and z components. Here we distribute the gammas into everything, and we can see that from that we can group the 0, 0's together and the 1, 1's together. That being said, we do that here, and we get a negative gamma squared, 1 minus beta squared, 0, 0, gamma squared, 1 minus beta squared, 1, 1, 2, 2, through 3. But what do we know about gammas? Well, that's equal to 1 over 1 minus beta squared. So the betas cancel. Betas cancel. And what do you know? We get a negative 0, 0, positive 1, 1, positive 2, 2, and positive 3, 3. Sure enough, they work out just as we want them to, and the transformation still remains on invariant. So yes, it is invariant, and we like to see that they remain the same before and after. These mathematical things turn up in the symmetry discussions that we have in later field theories, again using this notation. So it's actually really cool to see this stuff. We will touch back on these invariant style questions very soon. So it's worth understanding that invariant means before and after the transformation are the same thing, and that we can recover. And this will lead to a lot of insight later, I promise you. So until then, I will see you later.